everyone. After the commanding opening of first session, we are entering into the second technical session of today, which is based on device simulation by engineer Amit Saini, Technical Director, Cadre Design System, New Delhi. First of all, I would like to introduce engineer Amit Saini. He is currently working as a technical director of Cadre Design System. He is having more than 11 years of experience in TCAD-based semiconductor modeling and VLSI EDA custom design tools and SPICE. Previously, he worked as a consultant engineer for Springsoft, which is further acquired by Synopsys. He also worked as an application manager in IMS for Silvaco from 2008 to 2010. Before that, he served as an application engineer at Lattice Semiconductor in 2008. He was a research fellow from IIT Delhi in 2006 to 2008, and he completed his BTech in electronics from UP Technical University in 2005. Now, I would like to invite Engineer Amit Saini to please start the session. Sir.
Good afternoon, all of you. Myself, Amit Saini, and in this session, I will give you a brief introduction about our product that is for semiconductor device modeling. So in this session, I will cover basically our product that is for semiconductor device simulation and modeling. And the product we have, this is our product matrix. We have a semiconductor device simulator that name is Genius 2D and 3D device simulator. Then we have a interactive GUI, graphical user interface, that name is Visual TCAD, and a simulation workbench that name is Visual Fab. It's also a process simulator. Basically here in Visual Fab we are doing two type of works. One is a process simulation plus a simulation workbench. Then we have a modeling tool for advanced 3D device and circuit modeling, that name is GDS2 Mesh. What this tool do? What this tool do, basically this tool will model your device or circuit in 3D like this.
Hello.
Yes.
This is Naresh Kumar from SGT University, Gurgaon. Sir, there is some technical problem, I think. Your voice is disturbing. Similarly, video is also there is some disturbance.
सर आप रीलोड कर लीजिए सेशन अपना.
Pardon, ma'am?
राइट क्लिक करके रीलोड कर दीजिए.
Just a minute, ma'am.
I think the mic is the issue. Okay. Now, basically, GDS2 Mesh is a 3D modeler software. It basically provides an environment where you can model a single device as well as a small circuit in 3D. Like this is one of the example. Here, our tool required a layout. This is a mask file. This layout file, it required as an input file. This layout, customer is free to design on any of the layout software. We are also providing a layout software that name is Layout. Layout. So you are free to make your layout in this tool or any of the standard tool. Like if I open one of the layout here, This is one of the inverter layout. So it required a GDS file. So this is a tool where we can open any of this format like GDS2 mesh, Oasis, DXF, CIF, Gerber, all type of format it supports. So this layout we give as an input file to our software that name is GDF2 mesh, and we parallelly we give a process file, a rule file. Then the software will implement those process on this mask and develop a 3D profile like this. It's kind of virtual fabrication. You are free to see all this type of doping profiles. You are free to fabricate any of the semiconductor technology, like this is one of the large solar cell structure 300 cross 300 micron with the silicon with the bus basically this and having a surface textured. Then you can also model the package, like this is the silicon die in BGA package, plus this is again this is a some larger circuit in term of TCAD. This in term of TCAD it's a larger circuit that having 24 transistors. If we make a only layout, it's very small circuit, but when we model in 3D, it creates huge number of mesh. Then this is a image sensor with the photodiode. This portion is a photodiode portion, and these are the three transistor image sensor, basically 3T image sensor. This is a complete pixel. Then this is again a large circuit with the dual interlock cells that having more than 70 transistors. So basically this module, GDF2 mesh module, is used to model any of the device and circuit in 3D. Then we have a radiation effect environment. Using this environment, we can make our semiconductor devices as a radiation hardened devices. Those we can easily use in space as well as in biomedical or any of the radiation hardened application based requirement. Now in radiation hardened, we have a simulator that name is high energy particle simulator that name is GSIT. GSIT work in a graphical user interface that name is visual particle. Then we have a Monte Carlo simulator for radiation that name is Run SEU. And we have a space radiation environment. See, once we do the radiation, once we do some radiation hardened simulation, we require some data like what kind of particle we want to fall on our device. From where we get that data? Basically, that data either we get from some customer or from some real life environment, or basically we require some source to get that data. So we have a tool, Visual Orbiter. Visual Orbiter have different models for different space environment, like for geostationary orbit, for solar, for different things. We have our models, and accordingly it gives us information that in this orbit this much radiation is available. So based on that data, we perform a radiation hardened simulation on our semiconductor devices. Now Visual TCAD. Visual TCAD is a graphical user interface. Here we simply draw our device, do the simulation setup, and then visualize the results. Like this is a work area. Parallelly, what I will do, I just open the software. I will show everything within the software. Software support both environment, Linux and Windows. This is a Visual TCAD environment. Here we have options: device drawing, device simulation, circuit schematic, text document to write a program, XY plot to plot our results, spreadsheet, visualization to see the 3D structure, 2D visual to see 2D structures. Now, first of all, I just open device drawing. This is a work area. Here we draw our devices. This plus sign is a center coordinate. So in like this in PPT we have shown iron mass. Similarly, we make our structure in this black work area. It supports all type of polylines, all type of shapes are possible here. It's a simple CAD tool. Then the advantage of GUI is it automatically create a mesh. Meshing means the points on which solver will converge the equation and produce our results. So here in 2D software automatically make mesh. A very high quality mesh it automatically creates, like we have shown in this figure. All type of simulations are possible here, like DC, transient, AC simulation, device and circuit mix simulation, and then optical simulation. Optical simulation means when we are simulating solar cells, image sensors, photodiodes, any of the optoelectronic device. Then here we are free to change the advanced setup like boundary conditions, material parameters, physical models and solver options. This is one of the window for NMOS simulation. We first fabricate or draw this NMOS structure. Then we load this structure in a simulation environment. In simulation environment, we set up the electrode biasing, what type of simulation we want to perform. Accordingly, we apply biasing here. Then once we click on simulation, it will start the simulation and give the results in this format. All type of simulations are possible, as I already told you, like DC steady state sweep, transient, small signal, frequency analysis, device and circuit mix simulation, ray tracing in optical simulation. Like this is a setup for transient simulation. Here we can apply the pulse. Then once we are assured that whatever the device we have designed is working perfectly as per our requirement, if we want to use that device for device and circuit mix simulation, we have an option. Whatever the device or circuit we fabricate, like this is one of the inverter we have designed, so we just convert this our own designed device in form of symbol. We can create our own symbol library and then call this symbol for mixed mode simulation. Mixed mode simulation means here we are using our TCAD component or TCAD device plus other active and passive SPICE components. This is a window for AC simulation. All this simulation mode we change from this option. All this simulation mode we change from this option. Here we get all different type of simulation modes. This is a window for optical settings. If we want to simulate solar cell or a photodiode, we require an optical source, means a light source. Light source, it may be either monochromatic light source or a spectrum file. So we just define what type of light source we want to use. Then on device where we want to fall a light, from 90 degree or from some angle from 60 degree, we just basically give a coordinate of our device. And if we want to use any of the lens, we select the lens from the lens option, like concave lens, convex lens. Then we define this focal length, its lens related properties in the lens option. Similarly, this is a window if we want to change the material parameter. Material parameter means if we want to calibrate whatever the models are available in the software are already calibrated model, and the materials are also calibrated. But if some of the customer want to recalibrate its material parameter as per his requirement, he's free to do that calibration by changing the basic band related, impact related, mobility, optical, thermal, and traps related properties. You are free to change all this type of properties for a semiconductor material. For metal, only work function is required. For insulator, permittivity and affinity is required. So for insulator, if you want to change properties of SiO2, like you want to use high K dielectric, you have to change only band related parameter. In band, there are two properties. First is permittivity and other is affinity. Just write here permittivity, its value, affinity, its value. That property of that material get changed. Similarly, this is a window for optical not for boundary conditions. Basically, what type of boundary condition we want to use? We want to use ohmic contact, Schottky contact, or what type of contact we want to use. Accordingly, we change the contact type. Or if we want to connect any lump circuit like RLC circuit with our electrode, we can give its value here. This is a window to change the solver options if you want to change the mathematical part in our simulation. Like this is one of the top view of a SRAM structure with a we can say with a well contact. These are the well contacts. If I show you this structure, this will be this type of structure. I just remove the oxide, hide the substrate, and show the substrate. This is the SRAM structure after fabrication. If we remove the interconnect lines and pads, remove the metals contact, now this is the simple SRAM structure without I have hide the just a minute. This is the simple fabricated structure for SRAM. Right. Acceptor type and donor type. So this is the same structure with the well contacts. This is a cross section view. All this type of shape you can easily take from the simulator. And here you are free to design your device either using GUI method, graphical method, or by using a scripting method. This is the way we write a script. We write a script in text document. Then whatever the results we get all the results in form of spreadsheet. Now it's up to our requirement what we want to plot and what we require on x-axis, what we require on y-axis. Accordingly, we just select the columns and plot from the spreadsheet. I just skipping few of the slides. Well, that is related to the radiation hardened. Now GDF2 mesh I have already explained here. What we have done, we have created a mask. This mask we can create in using any of the software. Then we write a process rule, and the software will implement those process rule on the mask and develop a 3D structure. How software will do this? Software basically consider the mask, the layout as a XY plane, and then extrude the Z direction as per the process rule. As per the process rule, we just extrude the Z direction and make the object in 3D. Like here, this is a shrink and expand feature. So it supports all type. This is a different type of etching feature, isotropic and isotropic etching feature. Using shrink and means expand feature only. This is a GUI. In this GUI, we on the top of we just load a process file, different process file we load here, and then we select the process file, we select the process parameter, and then we give a mask file. In this option we provide a mask file. Then we just select the means whatever the process we select here, we get all the process parameters here, like it's showing here. Lambda means design rule length, thickness of the substrate, thickness of FTI, thickness of oxide, thickness of poly, like all these process parameters are visible here. If we want to change, we just double click here and change. If I show you the live image, this is live. Whatever we want to change, we just change in GDF2 mesh. Then whatever the layout we give as an input file, software read that layout. Software read each of the mask layer available in the layout, and then once we click on generate mesh, software will generate a 3D structure like this. You are free to make any of the 3D circuit like inverter, SRAM, D flip-flop, whatever the circuit you want to make. Every circuit you can fabricate in 3D here in this environment. Now what I will do before starting this session, I just want to show you some of the device galleries. Before starting our live demonstration, I just want to show some of the device galleries that you can easily design in TCAD environment. Like this is one of the SRAM. This is a simple PN junction diode. You can make simple from, I'm starting from PN junction diode. You can easily create PN junction diode. Then BJT, that is a bipolar junction transistor. This bipolar junction transistor is same. I just want to show to you. This simple BJT structure we have designed in tool. Similarly, I have like this we have shown here. This different color shows the different regions. Green color shows its N-type region. Yellow color shows its P-type region. So this is basically a emitter part. This is a base part. This is a collector part. PN junction diode, BJTs, then MOSFET. This is a MOSFET. This is a MOSFET structure with net doping. Then from MOSFET, this is an inverter. This is N-type MOSFET. This is P-type MOSFET. Both. This is a green portion is a well. Inside the well we make P-type MOSFET. From PN junction, MOSFET, BJTs, CMOS. Then we can move to advanced like we have here a FinFET structure. This is one of the FinFET structure, SOI FinFET. If I remove the side layer, this is a FinFET structure. This is a tri-gate FinFET structure. Then we can make advanced FinFET, like this is a stack gate, metal stack. This FinFET having bottom means gate is of copper and top gate is of polysilicon. This is a gate stacking. If I remove the nitride part, you see, and if I hide the this part also with metal, you are able to see. This blue color is high K dielectric, that is HFO2, and bottom gate is of copper and top gate is of polysilicon. So gate stacking we have done. Similarly, we have advanced structure with multi-fins. This is a multi-fin structure. Multi-fin with ultra thin body. This is very thin body. If we remove the oxide part, this is again a SOI structure. If we remove the oxide part, you are able to see. These are the three fins, and this is the very small UTB, very ultra thin body with along with the fins. If I remove the nitride also, we are able to see the gate electrode with gate oxide. Gate oxide material is HFO2 again, high K dielectric. Similarly, we can make gate all around structures like this. This is a gate all around structure. If I remove the left and right oxide, we are able to see the cylindrical structure. All this type of advanced MOSFETs we can easily design here. This FinFET structure. This is a gate all around. This is the ultra thin body FinFET, multi-fin FinFET. And this is a simple MOSFET in 3D. Simple MOS structure in 3D. And then the advanced CMOS based SRAM I've already shown. Now I'm showing you advanced SRAM structure. This is a FinFET based SRAM SOI device. This is again, I remove the oxide part, surface passivation layer. This is the FinFET. You see, this is the fin tri-gate. This is a FinFET based SRAM structure. So here we are giving an environment where you can work on any of the technology, traditional technology, older technology, or novel structures, from PN junction to any of the advanced structures. Now in this demonstration, what I will do, I will make one NMOS structure and then simulate its IV characteristics, then save that NMOS structure in form of a symbol, and then use that NMOS for circuit simulation. Means I will do a mixed mode simulation using CMOS. First of all, in this work area, we create a NMOS structure. This plus sign is a center coordinate. Now I just take a rectangular box from the device drawing options as shown in this left hand side, and then make a rectangular box like this. Then I make a contact pad for source, contact pad for drain, contact pad for back biasing, and gate electrode. Then what I will do, this is a side of means spacer, and I just close this gate portion. So in this way, I have just drawn a cross-section view of a MOSFET. Then what I will do, I will fill this cross-section view with different materials and add the doping. For adding different material, we first click in add region label. We click, we select here, we give the name silicon body, silicon meshing 0.05. Okay. Then this is an intrinsic type silicon. We haven't had any impurity here. Then we make source. This is a source pad, not a source region. This is a source contact pad. Similarly, we make drain pad, same material aluminium. And this is side spacer. This is again side spacer. Then this is gate n-type polysilicon, and this is gate oxide SiO2. Here we have a lift of material. Lift of material is here. This is a lift of material. All type of semiconductor materials are available in the library. Now we select SiO2 as a gate oxide. And similarly we add bottom electrode. Give the name bottom electrode BE, or we can give substrate electrode aluminium. Now our cross-section view is ready for NMOS. Here we have two formats. Currently it's a solid format and opaque mode. This is the opaque mode. This is a transparent format. So just change again this to solid format. Now like this. Okay. Now we add impurity here. Because currently our silicon is intrinsic type. So if we want to make n-type, we have to take our silicon body p-type. So what we do, we click on the add doping profile. We select the silicon. We add uniform doping. P-type, we give some name. Then acceptor, concentration 1E16, okay, and add the doping. Now once we add the doping, if we again show you the opaque mode, it will be like this, yellow color. Means our silicon is uniformly doped. Then we add source and drain region. Before adding source, okay, I will add source and drain region because we want to make an enhancement MOSFET. For enhancement MOSFET, we have to add VT implant layer in the beginning. So if we want to make if we don't add VT implant layer, it will be a depletion mode. So to make it enhancement, we add one more thin layer of P plus impurity on the top. We give the name VT, topping species, acceptor type only, depth 10 nanometer. Okay, this we called VT implant layer. Then we add lightly doped region for making source and drain. We first select this portion, Gaussian LDD for source doping. Any name we can give here. Donor 18, junction depth 5 nanometer. Okay. Again we repeat Gaussian source doping. This time it's a deep junction. Deep junction have higher concentration and junction depth. I give 25. Similarly, we repeat this same values for drain because source and drain both are identical in MOS technology. LDD for drain doping, we give the select the donor 1E18, junction depth 5 nanometer. Okay. Drain doping, donor 1E20, junction depth 25 nanometer. Okay. Now our doping is done. We save this structure, create one folder, NITR. We save my MOSFET. Give the name, whatever the name you want to give, you are free. You just give them my MOSFET and save this file. Then software will automatically make a mesh. Once we click on do mesh, we click do mesh, we want best mesh, software automatically make a mesh like this. I open magnifier. Like this is the mesh. It's visible there. Now once we click on this option, do refine mesh, then software automatically refine the mesh from the PN junction. We again click refine mesh, best mesh. We repeat this task for 2 times. Now what is the impact of this? The impact is this. See, the mesh is refined from the junctions. Mesh is refined from the PN junctions, means at the interface. From every side the mesh is refined. Now our device is ready. We just save this device. We click device, save mesh to file. We give the name MOSFET N. Click on save option. Then we open this. We open our file MOS. Change the panel settings. Our MOSFET is ready. Now we just open the doping, net doping. Now this is our device. Want to see the mesh? We click here. This is the mesh. See, it's refined from the PN junction. It's refined from the PN junction regions. Now we want to simulate this device. For simulation, what we do? We click on File, New. Previously, whatever we have done is in device drawing, and this output we have open in 2D visual. Now for simulation, we do we open device simulation, and device simulation. Just a minute. Okay. I think it's better. In device simulation, we just load the device, whatever we have designed. Okay. Minimize this black window. Take some time, depend on the mesh. Okay, start loading. Now our device is loaded here. This different color shows different regions. These all are the regions. There are different regions. Now want to see the material? We click on material. Now this is a material. Now what type of simulation we want to perform? Accordingly, we apply biasing here. Like if you want to perform ID VG simulation, for ID VG simulation, can I use this board?
Yes, sir.
I need marker and
So, what keyboard is it? Black.
black.
ऊपर का पोर्शन यूज करिए
हाँ, ऊपर
कैमरा में नहीं आएगा
For ID VG simulation means we simulate for ID VGS simulation we ramp. This simulation we will do, or this simulation we will do, we ramp the gate voltage and check the output here. ID, drain current. Okay. Now for this, what we do, we ramp. We apply a constant voltage, 1 volt, and ramp the gate voltage. Magnifier is visible there. Magnifier.
जो बाहर आ रहा है वही जाएगा
Okay, but magnifier दिख रहा है हमको?
नहीं
नहीं जा रहा ना, कहीं से बंद कर दें फिर. Now 0 to 2 volt in step of 0.05. Save this structure, MOSFET, and then I'm just taking by default settings. This is a window for boundary conditions. These are the different options. This is a window to change the models. So currently I'm taking by default model for this MOSFET simulation. Now if I run here, run, it asks for a folder. I just select this folder, NITTR folder, and the simulation is submitted. This black window shows the simulation is submitted. We get the option simulation job submitted. Now we click OK. Now on this left hand side bottom, we get the results. Here we get the results. And this is a window to check the console running or not. The option is available here to check the console. Parallelly, we also get the progress window on the right hand side. Now our simulation is running. 1 volt is completed. So during simulation, if you want to check the results, we select and right click. We click on open spreadsheet. Here we get the results in form of this spreadsheet. Then we select gate electrode because we are doing IDVG. So we are ramping the gate. So we select gate voltage and drain current. Refresh so that all simulation results get simulation job submitted. Okay. Simulation job submitted. Now right click, select right click. On x-axis we required voltage. So we select voltage and we get the IV characteristics like this. This is a linear scale. If you want to change the scale property, select here log scale. This is the log results. For plotting, here we have advanced tools also, like there is no need to use origin or any other tool. We itself have a very advanced feature for plotting, like this is one of the feature for plotting. Now the other feature is if you want to plot the same results, I just close those results and I open these results in 2D visual. I open 2D visual. Here I say load file. We select here .dat. We select results. Now these are the results. Then we click on edit plot option. Here what type of plot we want: Cartesian, polar, Smith chart, data coordinates, whatever type of plot we want. Accordingly we just select. Now curve plot, create. X-axis we require gate voltage. We select gate voltage. Okay. Y-axis we require this drain current. We just change the color, change the symbol, increase the size, and like this. Then if you want a gridding, we can show the grid, fine, more fine grid. Then log scale. Okay, to refresh it. Wait. Then there is an option, all ticks are outside. We have to make inside tick in. Now all ticks are inside, like these ticks. So these are plotting tool. I have to check the plotting option. It's not get refresh. There's some option, something is changing here. So that is not an issue. So here, from here, we can also change the syntax. What type of syntax we require? Everything is, whatever is available in origin, everything is available here. Now, after simulation, if we want to see anything within the device, we open this device in visualization. Previously, we have opened the results in spreadsheet. This time we are opening it in visualization. Visualization means we are able to see all these things within all these options within our device. Like if we saw the electron density, this is a log plot, this is a linear plot. If we see our electron density is high in source and drain region, but there is no channel in this portion. So once we play it, what it will do, it will increase the gate voltage. See here, the gate voltage start increasing, and once once the gate voltage, it will increase from the threshold voltage, the channel start forming. See, the channel start forming. The electron density start increasing in the gate region, means the channel is formed. In this way, we are able to see the electric field, the current flow, everything is visible here. Right, recombination, everything is visible here. Now, if we want to plot a conduction band and valence band at 0, when gate voltage is 0 and gate voltage is at 2 volt, for what we do, we just open 2D visual again. Now here we add VTU 0 file, result 0.VTU, and we also open 41 file. So these two files we open. Now, in these two files, we select conduction band and valence band and take a cut line, put a cut line in the MOS portion. MOS portion is gate oxide semiconductor. We put a cut line here. Okay, we haven't selected. We select this conduction band and valence band. Then we put a cut line. This is at when result is 0, and this is at when result is at 41. Now what I will do, I just select this, delete this, delete this, I select and try to merge. We're able to see the difference, band bending at 0 and 2 volt. The blue line initially, this is when it is at when gate voltage is 0, and this is when gate voltage is 2 volt. The conduction band start bending towards the Fermi level. So in this way we are able to plot any of the internal variable of a MOSFET. Like similarly, if you want to plot a electric field, I just delete it. Now similarly, if you want to plot an electric field, this is the electric field, this is the potential, electron density, hole density, everything. If you want to plot, we just take a cut line, put a electric field cut line in the, basically electric field is more in the gate oxide region. So in the gate oxide region, I just put, this is horizontally and this is vertically in both ways. Similarly, the electron density or a net charge, if we put, just remove this, in gate region, if we put a cut line, we are able to see the net charge. Any of the things we can easily plot, electron mobility, hole mobility, everything is visible, everything is possible to plot. And whatever we plot, if we require its data, like if we plot electron density, and we require its data, so we have option here, advanced data manager. So here we get all this data. Where we have put a cut line, all this data is available. So we can easily use this data for whatever the means, wherever we want to use it easily. Now what I will do, we have designed an NMOS, we have plotted its ID, its IV characteristics. If we want to plot its ID VD characteristics, like
सर गैप में मेरे जगह होते हैं
okay, if you want to plot its ID VD characteristics, when VG is 0.5, when VG is 1, when VG is 2 volt, assume. So if you want to plot this, we have to perform the simulation, we have to change the simulation setup. Now what we do, we change the simulation setup. For simulation setup, previously we have ramped the gate voltage and our drain voltage is constant, but this time what we do, we make gate voltage constant. We perform 3 different simulation as I shown in figure. For gate voltage 0.5, when gate voltage is 0.5, and gate voltage is 1, and when gate voltage is 2, we just sweep the drain voltage from 0 to, let's assume 2 volt in a step of 0.1. Save it, we run. It will take hardly a minute time to simulate for gate equal to 0.5. Now drain start ramping from 0 to 2 volt in step of 0.1. Now it's done. Now we open the results in spreadsheet again, and we select drain voltage and drain voltage and drain current, and just plot it. This is the initial when gate voltage is very low, means 0.5. It's almost at threshold voltage because our device is very large here. So what do we do? Whatever the results we get, we have plotted, and now we export these results. After export, what we get? We get a new spreadsheet. Why we export? Because we have to change this column name. So before we change this column name, I just again run the simulation for gate voltage 1 volt. I just increase the gate to 1 volt, save and run. Okay, running. Now by the time this simulation will be over for gate equal to 1 volt, we just change the name. Why we are changing the name? Because we require this same for the drain current for different gate oxide for gate voltage. So we give here the name drain current when VG is 0.5 volt. Okay. Now we again plot the new results. This is the new results. We again copy this new drain current and paste here in the adjacent column. We copy and paste here. Again change the name, Control C. Now this is for 1 volt, gate equal to 1 volt. Close. We again run when gate is 2 volt. To start, now this time it will ramp gate for 2 volt. Now start ramping the drain. Now we again, first of all, this simulation will be complete. See here the drain is ramping from, it's about to finish. Now this finish. Now we again copy the drain. Okay. We can copy and paste here in new column. We again change the name. 2. I will select discrete drain current when gate voltage 0.5, 1 and 2 volt. Along with drain voltage, we plot. So this is the way we plot the IDVD. See, initially the black color means the gate voltage is very low, 1 volt, the pink color. What I will do for get a better curve, because our device threshold voltage is high, so that's why we are not getting proper current when gate voltage is 1 volt. So what we do, we just again perform one new simulation for gate voltage 1.5 volt. This remain okay. Gate voltage 1.5. Again run this. Now start increasing the drain. We open the spreadsheet again. Okay. Copy this, paste here, and change this name 1.5 volt. Now we again plot. See the ID VD of MOSFET with different gate voltages. Now if you want to perform a mixed mode simulation for the same device, what we do, we convert this device in form of symbol. So how we convert? We move back to setup environment. Here we change the simulation mode to circuit element. Now we change this symbol for n, whatever the symbol we want to select. This is a customizable library. We are free to customize this library as per our requirement. Now we lock the pin S with source, G with gate, D with drain, and B with a back electrode substrate. We save this file. This file is MOSFET.sim file. We save this file and then call this file in circuit schematic. For mixed mode simulation, we open circuit schematic option. In circuit schematic, we call our saved device that we call numerical device. Numerical device, that is MOSFET.sim. Call this device. Then mixed mode simulation means we are taking our fabricated MOSFET as a numerical device, and we are taking a PMOS as a library component, a SPICE component. PMOS from the library. This is the model. Now we make a connection using the wire. This blue one is model and black one is TCAD component. Now we make a connection. Take a ground. take our source. For transient simulation, we take pulse. For DC, we take DC. So I take pulse. We perform a transient simulation. For power supply, we take VDC source. Then we take a wire. We make connections. Now this tool will work as simple design tool like other tools works. The only difference is here the component, whatever the component we are using is our own designed component. We are free to change its oxide thickness, dimensions, doping concentration, everything we are free to change now. But here this is a 2D device. For 2D device, by default width is 1 micron. I just want to show you global parameter. By default width is 1 micron. So if you want to change the width, either we change from here and save it, or accordingly we have to make our width. Just close this old files. Now here for PMOS, we just give 180 nanometer and width is 2500 because the PMOS width is normally 2 or 2.5 times more than NMOS. That's why by default width of NMOS is 1 micron, so increase 2.5 times width of PMOS. Now we add a probe, voltage probe, to see the results. This is our results. Now we apply a source 2 volt to the input, and here apply 2 volt. We make a pulse lifetime 4 nanosecond, fall time lifetime 1 nanosecond, fall time 1 nanosecond. Okay, I'm just reducing the pulse width. Pulse width I'm taking 3 and 1, 4. Total pulse width is 3, 6, 7, 8. 8 nanosecond. Okay. Now I just save this file, CMOS, and run this simulation. Before running this simulation, because my pulse width is of 8 nanosecond. Suppose I want to see the result for 1 pulse only, so I give time period simulation time 8 nanosecond. If we require 2 pulse, we give time simulation time 16 nanoseconds. So let's suppose we take 2 pulses. So I give stop time 2 nanosecond. I will take output for 2 pulse 16 nanosecond. Time step 0.1 nanosecond. Maximum time step 1 nanosecond. Okay. Save. Now we run this. Okay, simulation submitted. We just minimize this black window. Simulation job submitted. Okay. Now we open the simulation results. See the console. Now this time we are doing transient simulation. So in transient simulation, what it do? It first start increasing the input, ramping the input pulse from 0 to 2 volt. So what I will do in transient simulation, I will show you both. I will show both results, DC as well as transients. Because when input is ramping, if we plot the output at the same time, we get the DC characteristics also. So I just open the spreadsheet. Here my input is V1, output is prop1. So we select input V1 positive and prop1 positive. You're able to see, refresh. See, my input is ramping and output reducing. Pink color is the output. I'm just currently simulation is running, so I'm just plotting our results during runtime. See, input is ramping from 0 to 2 volt. Okay, see the DC characteristics is almost, this is a DC characteristics for an inverter. Just refresh. See the DC characteristics for an inverter. Now once the pulse will be complete, we get the transient response. This is a kind of DC characteristics for an inverter. Now the current, I just update the simulation results. See, if we see only this portion, when the input is ramping from 0 to 2 volt, this will our DC. Now simulation. Now the input is ramping again from 2 to 0 volt. Mixed mode simulation will take some time because we are doing transient simulation. Here, this is the log file. The simulation is running. You just refresh the result file and then refresh the plot file. See, from 0 to 2 volt and from 2 volt to 0. Okay, almost one pulse completed. They have given a pulse of 8 nanosecond. Now one pulse is completed. The second pulse will start after this. The second pulse started. Okay. See, the second pulse started and we are again getting 1. We are giving input 1, we are getting output 0. It's means our inverter circuit is behaving properly. So in this way, we can do the mixed mode simulation. Now I'm just closing this session. Before that, I just want to show you how we design our 3D devices. There are two methods to design our 3D devices. If we want to design a 3D single device means this structure, this kind of FinFET structure or a nanowire structure. Then we have to write a script. The script will be like this. The script will be like this. We have to define mesh, region. In region, we have to fill different materials. Then doping information. We have to write a code like this. It's a device. This program we call device deck. And once our device deck is ready, we simulate our device deck from this option, run as Genius deck. So we get the results after simulation, means that the structure will be like this. Now, if we want to make a 3D or want to fabricate a 3D circuit, for circuit the primary requirement is layout. Like this is one of the inverter layout. If you want to fabricate this layout, first of all we require a layout, that is a mask. This layout we are free to design in any of the standard tool like K-layout, Cadence, Mentor, Synopsys, any of the environment. We require a GDS file. Then this GDS file we give to our module GDS to mesh. Here we add the file like this. This is the D flip-flop half adder. Let's we take half adder. Process we select whatever the process we are providing up to 12 nanometer FinFET process. So here I'm selecting 180 nanometer currently. And create a mask. Half adder. Okay. Okay. This is a half adder layout. Now once I click here, once I click on generate mesh, software will implement all this 180 nanometer process parameter on this mask and make a 3D structure of this half adder. Okay. Like this, it will start building the structure. It will take some time. So what I will do, I just show you what kind of structure it will give as output. I think I have already shown to you the SRAM structure. It will make the 3D structure for half adder will take something around 15-20 minutes to simulate. By the time I just show you the SRAM. The structure will be like this. This is the output format for GDS to mesh. Means this kind of advanced structures are possible only through layout. It having 6 transistor with multi-metal interconnect, vias, pads, everything is available in here. So this is the output of GDF2 mesh. GDF2 mesh will give us an environment where we can fabricate our layout. This is all about this session. If you have any query, please feel free to ask.